Why do we need semiconductor materials for solar cells? This week, I discussed the important properties of semiconductors and how these properties are being used in solar cells. This means that we have to take a tour in the world of physics. This week will be the most theoretical part of the course, but don't worry, I will guide you through it, using some visual figures and animations. Let's start with answering the question, what is a semiconductor material? Materials can be categorized in terms of their electrical properties. Let's consider metals. We know that metals can conduct electricity very well. The origin of the high conductivity of metals is based on the fact that the outer electrons of the atoms in a metal are weakly bound. This results in an ocean of free mobile electrons in the material, indicated by the red dots. Electrons are negatively charged, and therefore the conduction in a metal is based on mobile negative charge. These electrons move around in a background of atoms indicated by the blue dots. As many of the atoms donated an electron, they can be considered as fixed, positively charged ions. Materials which do not conduct electricity are called insulators. In insulator materials, the ocean of free moving electrons are missing. All electrons are bounded to the background atoms. As you can see in the figure, the red dots represent the electrons and are glued to the blue atoms. Semiconductors are materials which have a conductivity between that of a metal and insulator. The outer electrons of the atoms are more strongly bound to the background atoms than in metals, but under certain conditions, some of the electrons can leave their background atom and become freely mobile electrons as well. These few electrons that are separated from its atom leave a positively charged entity behind. This positively charged entity is called a hole. The small blue dots in the illustration represent the holes. These holes are able to move around just like the electrons. As a result, the charge transport in a semiconductor is facilitated by negatively charged electrons and positively charged holes. The property of metals, insulators, and semiconductors can easily be illustrated using electronic band structure of a material. An electronic band reflects the potential energy levels an electron could occupy in the material. Metals have a broad electronic band which is not fully filled with electrons. This electronic band corresponds to the energy levels in which the electrons can freely diffuse around in the metal. An insulator and a semiconductor, to the contrary, have two distinct bands with a large forbidden gap between them. Most electrons fill the lower electronic band, the so-called valence band. If electrons reside in the valence band, they are not mobile. They are well bound to the atoms in the lattice. The upper electronic band is the so-called conduction band. Electrons in the conduction band are free and mobile and contribute to the conduction, just like the mobile electrons in a metal. The forbidden energy gap between the valence and conduction band is called the band gap. In this gap, no energy states exist, which can be occupied by electrons. The difference between insulators and semiconductors is that the band gap of an insulator is much larger than the band gap of a semiconductor. The band gap of an insulator is typically larger than 3 electron volts. The larger the forbidden gap, the smaller the probability that an electron can have enough energy to occupy a state in the conduction band. For a semiconductor, the band gap is smaller. If the band gap of a material is smaller than 3 electron volts, the material can be considered to be a semiconductor. In a semiconductor, some electrons can have enough thermal energy to jump from the valence band to the conduction band. This energy can also be provided by light, if the photon has an energy equal or larger than the band gap. This means that when you shine light with photons having an energy larger than the band gap, you can make a semiconductor more conductive. The blue dots located in the valence band represent a positively charged hole, while electrons in the valence band are glued to their background atoms. The positively charged holes can diffuse through the valence band just like the electrons in the conduction band. So up to this point, I have introduced the basic properties to describe semiconductor materials. The conductivity properties are determined by the electrons in the conduction band and the holes in the valence band. The energy gap between the conduction and valence band is called the band gap. The question now is, what is the principle behind the existence of the forbidden band gap between the valence and conduction band? Or, in other words, what determines how strongly the electrons are bound to the atoms in the lattice? I will discuss that in the next 2 blocks. First, in the next block, we will look at how electrons are bound to the nucleus within an atom. What is the principle of a band gap? It's not straightforward to quickly explain this principle, but I will give it a try. I will use a chemical picture to explain the nature of the band gap. You have to realize that I will make some crucial simplification in explaining the nature of the band gap, so don't tell it to your physics and chemistry professors. First, we have to consider the question, how do electrons bond in an atom? As silicon is the most important material for current solar cells, we're going to look how electrons are bound to the nucleus of a silicon atom. Before we will discuss the silicon atom, I'm starting with the most simple atom in our universe, the hydrogen atom. The hydrogen atom has a nucleus consisting of 1 proton. The proton is positively charged. Around this proton, the much lighter electron is moving in orbits. The electron is negatively charged. This relatively simple system can be described by complex laws of quantum mechanics, like the well-known Schrödinger equation. I won't go into detailed physics, but the only thing you have to know at the moment is that quantum mechanics and the Schrödinger equation tells us that the hydrogen atom, the electron, can only occupy certain discrete energy positions. The lowest energy position is the ground state, indicated by 1s. And the electron is strongly bound to the proton. It's on average in orbit close to the nucleus. This energy level is in the so-called first electron shell. If we give the electron more energy, it can be excited to a higher energy level, to the second shell. The electron is less strongly bound to the atom, and its average orbit is further away from the nucleus. In the second shell, we find 2 types of electronic energy levels, 2s and 2p. If we give the electron even more energy, it can be excited to the third shell. The strength of the bond between nucleus and electron is further reduced, and its average orbit around the nucleus is even further away from the nucleus than for the orbits in the second shell. In the third shell, 3 types of electron states are present. However, in this course, for simplicity, we only consider 2 types of electronic energy levels, 3s and 3p. Here, The electronic orbital of the electron in the ground state is shown. The orbital reflects the volume in which the electron might be present during its journey around the positron. On the left, you can see the three-dimensional representation of the orbital, and on the right, you can see the two-dimensional representation of the orbital. The orbital of the 1s ground state is symmetric in all directions and has the shape of a sphere. The orbital of the 1s ground state is symmetric in all directions and has the shape of a sphere. The orbital of the excited 2s state is a symmetric sphere as well. However, the sphere is larger, indicating that the electrons are in an average orbit at a larger distance from the nucleus. The orbital, referred to as 2p, has asymmetric shape and in a rough approximation consists out of two lobes. Due to the asymmetry, it can be described in three different directions: the x, y, and z direction. Consequently, three different 2p states exist. We can also go up to the third electron shell, in which the orbital corresponding to the 3s is again symmetric and much larger. The electron is less bounded to the nucleus and its average orbit is further away from the nucleus. The 3p orbital is again asymmetric and starts to consist in rough approximation out of four lobes and has three different states. These discrete energy levels can help you understand how the periodic table of elements is built up. Before we do that, we have to discuss one important additional property of the electron and one important law of the quantum mechanics. The important property of the electron is that electrons can have spins. The important law in quantum mechanics is the Pauli exclusion principle. First, electrons have spin. What is a spin? Let's consider a charged body in classical electrodynamics, like these spheres. We start to rotate these bodies. The rotation of the charge will induce a magnetic dipole. Depending on the rotation clockwise or counterclockwise, the magnetic dipole will point up or will point down. This concept appears to be still valid for a little tiny electron, with having the smallest charge possible, the elementary charge. This means that an individual electron can be in two quantum states: spin up and spin down. Secondly, I introduce the Pauli exclusion principle, which tells us that two identical electrons cannot occupy the same quantum state simultaneously. Don't worry about why this is the case, just for the moment accept that in nature all electrons obey this law. Now let's consider two electrons which both are in a state with their spins up. Can these electrons both fill the same energy state x? The answer is no, as both electrons have the same spin and they have the same energy. This means we have two identical electrons that occupy the same quantum state, and this violates Pauli's exclusion principle. Now let's consider two electrons which have opposite spins, one spin up and the other spin down. Can these electrons fill the same energy state x? In this case, the answer is yes. Although the electrons have the same energy state, the electrons are not identical as they have different spins. Pauli's exclusion principle is not violated and these two electrons fill the same energy level. Basically, Pauli's exclusion principle allows every electron energy level to be filled by at maximum two electrons. Using this knowledge, let's consider the next element in the periodic system, the helium atom. In its nucleus, it has 2 positons and 2 neutrons. Since neutrons do not have a charge, the charge of the nucleus is determined by the 2 positively charged positons. Around the helium nucleus, 2 electrons are in orbit. This system has similar electronic states in the first and second and third shell as the hydrogen atom. One of the electrons has a spin up, as indicated with the red arrow up. One electron has a spin down, indicated with the red arrow down. Following the Pauli's exclusion principle, both electrons can be in the ground state. This means that a helium atom in its ground state has its 1s level fully filled. If we now move to the next element in the periodic system, the lithium atom, the nucleus has besides 3 neutrons, 3 positrons and 3 electrons in orbit around its nucleus. Following the Pauli's exclusion principle, the third electron cannot join the 2 other electrons in the 1s ground state, because whether it has a spin up or a spin down, it always will be identical to one of the other electrons in the ground state. As a result, the third electron will fill the next lowest state, which is the 2s state. The next element in the periodic system is beryllium, which has 4 electrons in the orbit around the nucleus. These 4 electrons fully fill up the 1s and the 2s electronic states. The next element is boron. It has 5 electrons in orbit and can fill up to 1 electron in the 2p state and has a total of 3 electrons in the second shell. The next element is carbon. It has 6 electrons in orbit and can fill up to 2 electrons in the 2p states and has in total 4 electrons in the second shell. So basically, carbon has its second shell not fully filled. As we discuss in the next block, the electrons in not fully filled outer shell are responsible for making the bond with other atoms in molecules or solids. As carbon has 4 electrons available in the not fully filled shell, carbon can make 4 covalent bonds like in methane gas or in diamond. The next element is nitrogen. It has 7 electrons in orbit around the nucleus and can fill up to 3 electrons in the 2p state. The next element is oxygen. It has 8 electrons in orbit around the nucleus and can fill up to 4 electrons in the 2p state. Fluorine has 9 electrons in orbit around its nucleus and can fill up to 5 electrons in the 2p states. Neon has 10 electrons in orbit around its nucleus and fills up the 2p fully with 6 electrons. Neon fills up fully the first and second shell. We also know that neon has very low chemical reactivity, similar like helium, which fully fills up the first shell. Both elements belong to the noble gases. This indicates that atoms with only fully filled shells cannot easily make bonds to other atoms, to make molecules or even solids, while atoms with not fully filled outer shells are able to make bonds. The next element, sodium, fills the 3s state with 1 electron. The magnesium fully fills up the 3s state with 2 electrons. Aluminium fills up 3p state with 1 electron. Finally, we arrive at the most important element for photovoltaic applications, silicon. 90% of the commercial available solar panels is based on silicon. Silicon has 14 electrons in orbit around its nucleus and fills up to 4 electrons in the 3s and 3p states. These 4 outer atoms are the weakest bound to the nucleus. Similar, like in the case of carbon, the 4 outer electrons of the silicon atom will play an important role in making bonds with other atoms in a molecule or in a solid. How do these molecular bonds determine the band gap of silicon? I will give the answer to that question in the next block. We have arrived to the question, how do molecular bonds determine the band gap? We have discussed that the silicon atom has 4 outer electrons. These 4 outer electrons play an important role in making the bonds with other atoms in a molecule or in a solid. These electrons are the so-called valence electrons. In a very cruel simplification, a bond can be considered as the mixing of 2 orbitals of neighboring atoms. One valence electron shares its orbital with the orbital of a valence electron of a neighboring atom. This means that it takes 2 valence electrons to make 1 valence bond. This resulting orbital is called a molecular orbital. From nature we know that the orientation of a silicon bond is tetrahedral-like. Consider the lattice of crystalline silicon, which is a diamond cubic crystalline lattice. Looking at a single atom in such lattice, the angle between all 4 bonds is 109 degrees. However, if we look at the orbitals of the 4 valence electrons in the 3rd shell of silicon, we don't recognize the tetrahedral coordination. Their shapes do not match a tetrahedral coordination at all. How are these states related to the orbitals? To explain this, we consider 1 electron in the 3s state and 3 electrons in the 3p state. We now make a cocktail of orbitals. We will mix these 4 states. In nature, it appears that these 4 states mix into effective 4 symmetric states. The animation demonstrates the mixing. The 4 resulting symmetric states are called the sp3 hybrid. In nature, the 4 valence electrons behave like they are in these 4 sp3 orbitals. The orientation between these 4 orbitals corresponds to the tetrahedral coordination with an angle of 109 degrees between them. Now we can roughly understand the coordination of the lattice of crystalline silicon, but still don't understand the origin of the band gap. For that, we have to look in more detail to how a bond is made between 2 atoms. Here you see 2 sp3 orbitals of 2 neighboring atoms, which are at a far distance from each other. Both orbitals have 1 electron at a discrete energy level that resembles that of the sp3 hybrid. To establish a bond, the 2 atoms have to approach each other. The orbitals start to overlap and merge into one molecular orbital with its own shape. Here again, the Pauli exclusion principle starts to play a role. 2 identical electrons cannot occupy the same quantum state simultaneously. Nature splits the original sp3 energy levels up in 2 energy levels. The lowest energy level is the bonding level and is lower in energy as the original 2 individual sp3 levels. As a result, both electrons prefer to fill this state, in which 1 electron has a spin up and the other electron has a spin down. This bonding state represents the attraction between the silicon atoms and the creation of a bond. The energy level of the bonding level is lower than the original sp3 level and therefore more stable. The second high energy level is called the anti-bonding level. The energy level is higher than the original sp3 level and therefore electrons do not prefer to fill this state. Another important aspect of bonding and anti-bonding levels is that the closer the 2 neighboring atoms are together, the larger the energy splitting between the bonding and anti-bonding level will be. This is demonstrated in the animation. Let's consider the example of silicon again. For silicon, the far majority of electrons will fill up the lowest bonding state. These lower bonding states reflect the valence band as introduced earlier. The anti-bonding states correspond to the conduction band and is hardly occupied by any electrons. The gap between the bonding and anti-bonding states corresponds to the band gap. If we look at the molecular orbital, its bonding and anti-bonding states are discrete energy levels. However, if we look at a solid like crystalline silicon, its network contains many silicon-silicon bonds. All these bonding states do not appear as one single discrete energy level, but spread their energy levels continuously over a broader electronic band, like the valence band or conduction band. Physicists, in general, use the term valence band, conduction band, and band gap. Chemists might use different terms for the same concepts. They might use the expression highest occupied molecular orbital, the HOMO, as the valence band, and the lowest unoccupied molecular orbital, the LUMO, as the conduction band. The HOMO-LUMO gap would be the band gap. So far we have discussed the situation for silicon, which is an element with 4 valence electrons. Carbon and germanium are elements which have 4 valence electrons as well. Carbon has 4 valence electrons filling the second shell, and germanium has 4 electrons partly filling the fourth shell. Carbon, silicon, and germanium all have tetrahedral coordination and form a diamond cubic crystalline lattice in its crystalline phase. Silicon and germanium can be considered as 4 semiconductor materials. The 4 stands for the number of valence electrons. Why is carbon not a semiconductor as it has the same lattice? To answer this question, we have to consider the bond length between the atoms, or in other words, to which extent the neighboring orbitals forming the molecular orbital are pressed together. The bond length is in general expressed in terms of lattice constant. What is the relation of the lattice constant and the bond length for a diamond cubic crystalline lattice? In this figure, the unit cell of a diamond cubic crystalline lattice is shown. The edge length of this cube is equal to the lattice constant. In diamond crystalline lattice, the lattice constant equals to 4 times the silicon-silicon bond length divided by the square root of 3. In the next graph, we plot the band gap of crystalline carbon, silicon, and germanium versus the lattice constant. Crystalline carbon is another name for diamond. We indeed see that the band gap is very large for diamond, as diamond has the smallest lattice constant. In a very simplified representation, the larger the band gap can be considered as a larger overlap of the original sp3-like orbitals of the neighboring atoms. A larger overlap induces a larger splitting of the energy levels of the bonding and anti-bonding level. Materials with semiconductor properties can be made from other materials than elements with 4 valence electrons. Let's consider the so-called 3,5 semiconductor materials, like gallium arsenide. 3,5 semiconductor consists out of 2 elements. One element has 3 valence electrons, the other element has 5 valence electrons. These materials can, similar to silicon, form a diamond cubic crystalline lattice. In the crystalline lattice shown here, the gallium are the blue atoms and the arsenide are the red atoms. The difference with silicon is that every gallium atom is neighboring 4 arsenide atoms, and every arsenide atom is neighboring a gallium atom. Let's consider the 3,5 materials based on gallium, like gallium phosphor, gallium arsenide, and gallium stibium. Again, the larger the lattice constant of the material, the smaller the band gap will be. Gallium phosphor has the smallest lattice constant and therefore the largest band gap. Another group of semiconductor materials are the so-called 2,6 semiconductor materials, like cadmium tellurium. 2,6 semiconductors consist out of 2 elements. One element has 2 valence electrons, the other element has 6 valence electrons. These materials can form a diamond cubic crystalline lattice as well. In the crystalline lattice shown here, the cadmium atoms are the blue atoms and the tellurium atoms are the red atoms. So every cadmium atom is bonded to 4 tellurium atoms, and every tellurium atom is neighboring a cadmium atom. Let's consider the 2,6 materials based on cadmium, like cadmium sulfur, cadmium selenium, and cadmium tellurium. Again, the larger the lattice constant of the material, the smaller the band gap will be. Cadmium telluride has the largest lattice constant and therefore the smallest band gap. I hope you have become familiar with the important properties of semiconductors, like the valence band, the conduction band, and the band gap. And I have shown that we have different semiconductor materials like silicon, germanium, gallium arsenide, and cadmium telluride. Important to remember is that all these semiconductors have different band gaps. So, how can we make semiconductor materials conductive? Or in other words, how can we fill the conduction band with free electrons? It's my pleasure to show that in the next block. How do we make semiconductors conductive? As discussed so far this week, we need to excite electrons from the valence band to the conduction band to make semiconductors conductive. This can be achieved by several different routes. First, we can excite charge carriers using thermal energy. Secondly, we can use impurities in the semiconductor material. This is what we call doping. The third option, which is very important to solar cells, is to use the energy in light to excite electrons from the valence band to the conduction band. Before I will discuss these various routes to excite charge carriers, I will first discuss the important concept of the Fermi level. Let's consider a metal. Electrons are filling the electronic band of a metal. The electronic band is a band of continuous energy levels. This band is not fully filled by electrons. The probability to find an electron is not the same at all energy levels. At low energy levels, you will have a probability of 100% that electrons fill this level, while at high levels, this probability is close to 0. The probability to find an electron can be expressed by the Fermi-Dirac distribution function. This function reflects the probability that an electron will occupy a state at an energy E. Low in the valence band, this function is equal to 1, whereas high in the conduction band, this function is equal to 0. Note that this equation is only valid for a material that is at thermal equilibrium, which means that no additional energy is coupled into the system by electrical biasing, light absorption, or heat conductivity. The Fermi level represents the energy level at which the electrons have a 50% chance to occupy the energy level at any given time. For a metal, it's easy to see where the Fermi level is positioned. Physicists use in general the term Fermi level. Chemists might use a different term. They might call this level the total chemical potential of an electron. The shape of the Fermi-Dirac distribution does change with temperature. At absolute zero, which means a temperature of 0 Kelvin or minus 270 degrees Celsius, the function looks like a step function. The probability to occupy a state below the Fermi level is 100%, whereas the probability above the Fermi level is 0%. For higher temperatures, this distribution starts to broaden around the Fermi level. Around the Fermi level, the energy is distributed over values between 0 and 1. The higher the temperature, the broader the distribution around the Fermi level will be. As you can see, a metal has only one electronic band. However, for semiconductors, this situation is different. The valence band is almost fully filled with electrons, whereas the conduction band only has a very few electrons. The Fermi level is positioned in the forbidden band gap between the valence and conduction band.
According to the Fermi-Dirac function, electrons have a 50% probability to occupy the electronic states at the Fermi level. Since no electronic band exists at this level, in the forbidden band gap, no electrons can occupy this level. So the real distribution of electrons over the two electronic bands become more complicated. In general, the Fermi-Dirac function shows that the energy levels in the conduction band have a low probability to be occupied, while the energy levels in the valence band have a high probability to be occupied. At absolute zero, a temperature of 0 Kelvin or minus 2070 degrees Celsius, all electrons fully occupy the valence band. The semiconductor material is not conductive. If we increase the temperature, the shape of the Fermi-Dirac function broadens around the Fermi level and some electrons have the chance to occupy the conduction band as well. The higher the temperature, the more electrons can occupy the conduction band. This demonstrates the physical principle that if you heat up a semiconductor material, it becomes more conductive. Using the Fermi-Dirac function, you can tell something about the distribution of holes in the conduction band as well. The positions in the valence band at which the electrons are missing are the locations at which the holes are present, indicated by the blue dots again. So if we remove the fixed electrons in the valence band, we are left with only the mobile charge carriers, the free electrons and the free holes. 1 minus the Fermi-Dirac function shows for a semiconductor the probability that you will find a hole at a certain energy level. This week, we will focus on the behavior of the charge carriers, electrons and holes in a semiconductor. We will use the semiconductor material silicon again as an example. And again, I will make a drastic simplification. The silicon network is a three-dimensional network, as you can see in this animation. The blue spheres represent the silicon atoms and the red dots represent the valence electrons in the molecular orbitals which are forming the bonds with the neighboring atoms. To illustrate the behavior of charge carriers in the silicon lattice, I will flatten the material and consider the silicon lattice to be a two-dimensional squared lattice. In this two-dimensional network, every silicon atom has 4 bonds with its neighboring silicon atom, like it has in a three-dimensional network. In this schematic silicon network, we put some charge carriers. The animation shows the mobile electrons, which again are indicated with the red dots. Secondly, we show the holes, which are in this illustration indicated by the black dots. They are part of a molecular bond in which one of the 2 valence electrons is missing. Both electrons and holes can move freely around. So far, we have discussed that we can manipulate the density of the free charge carriers using temperature. The higher the temperature, the more free electrons and free holes can be excited. Another approach to increase the density of the charge carriers is using doping. Up to now, we have considered pure semiconductor materials without any impurities. These semiconductor materials are called intrinsic. It means that the density of the mobile electrons and holes are the same in the material. We can intentionally incorporate impurities in the material. This is called doping. Doping can have a significant effect on the charge carrier density, which I will explain now. As an example, we take again silicon. Silicon is a material which has 4 valence electrons. In the periodic system, silicon is part of the column with atoms having only 4 valence electrons. At the left side of the column with 4 valence elements, we see that we have materials with only 3 valence electrons, like boron, aluminum, and gallium. On the right side of the silicon in the periodic table, we have atoms which have 5 valence electrons, like nitrogen and phosphorus. First, we are going to intentionally put phosphorus impurities in the silicon network. Phosphorus has 5 valence electrons. The phosphorus atoms will make molecular bonds with its 4 neighboring silicon atoms. Since the phosphorus atom has 5 valence electrons, it has 1 electron left. This extra electron is easily excited to a free mobile state. The phosphorus atom left behind is not neutral anymore and becomes a positively charged entity. This positive charge is fixed to the position where the phosphorus atom is residing in the lattice. The result is that by adding an impurity, we have 1 extra free mobile electron and a fixed positive charge in the background. This is called n-doping. For n-doped semiconductors, the electrons are called the majority charge carriers, as the density of the electrons is much higher than that of the holes. The holes are called the minority charge carriers in an n-doped semiconductor. N-doping of silicon can also be illustrated by an electronic band diagram. The phosphorus atoms are represented as donor states. These donor states have an energy level within the forbidden bandgap of the silicon matrix, which can be occupied by electrons. The energy level of the donor states is closer to the conduction band than to the valence band. This means it requires much less energy for an electron to jump from the donor state to the conduction band than for an electron from the valence band to the conduction band. At typical room temperatures, many to all of the electrons in the donor states can be excited to the conduction band. As a result, we have more free mobile electrons than mobile holes in an n-type semiconductor. We call the states donor states because they donate an electron to the conduction band. The electrons are the majority charge carriers. The holes are the minority charge carriers. As the electrons are the majority charge carrier, the Fermi level will be closer to the conduction band than to the valence band. Secondly, we are going to intentionally put boron impurities in the silicon network. Since the boron atom has only 3 valence electrons, it is missing 1 electron to make a molecular bond with its 4 neighboring silicon atoms. As a consequence, 1 molecular bond is filled with only 1 electron. This entity is the same as the hole. This extra hole is easily excited to a free mobile state as well. The boron atom left behind is not neutral anymore, but becomes negatively charged. This negative charge is fixed to the position where the boron atom is residing in the lattice. The result is that by adding a boron impurity, we have 1 extra free mobile hole available and 1 fixed negative charge. This is called p-doping. These states are called acceptors, as it accepts 1 electron from the valence band. For p-doped semiconductors, the electrons are called the minority charge carriers, as the density of electrons is much smaller than the density of the holes. The holes are the majority charge carriers in p-doped materials. P-doping of silicon can be illustrated by an electronic band diagram as well. The boron atoms result in acceptor states. These acceptor states have an energy level within the forbidden bandgap of the silicon matrix, and the acceptor states can be occupied by electrons. The energy level of the acceptor states is closer to the valence band than to the conduction band. This means that it requires much less energy for an electron to jump from the valence band to the acceptor state than to the conduction band. For silicon at room temperature, many electrons of the valence band can be excited to the acceptor states. As a result, we have more free mobile holes than mobile electrons in a p-type semiconductor. The electrons are the minority charge carriers, the holes are the majority charge carriers. As the holes are the majority charge carriers, the Fermi level will be closer to the valence band than to the conduction band. Let's get a feeling for the typical concentrations for majority and minority charge carriers in doped silicon networks in the dark. Typical densities for majority charge carriers in silicon are 10 to the 16 per cubic centimeters, whereas the density of minority charge carriers in that case would be 10 to the 4th per cubic centimeters. This shows that the density of majority charge carriers can be many orders of magnitude higher than that of the minority charge carrier. Note that the silicon density in crystalline silicon is 5 times 10 to the power 22 per cubic centimeters. This means that the total number of charge carriers is much lower than the typical density of silicon atoms. The ratio majority charge carriers to silicon atoms in this example is 1 to 5 million. The density of charge carriers can be described by the law of mass action. What does this law mean for charge carriers in semiconductor materials? This law tells us that at a given temperature, the product of the electron density and the hole density is constant, independent of the doping concentration. If N corresponds to the electron density and P corresponds to the hole density, this law tells us that the product N times P is constant, if we would manipulate either N or P. So let's consider intrinsic silicon. This is silicon without any impurities. At room temperature, the electron density N and the hole density P are equal. For silicon, the electron and hole density is in the order of 1.1 times 10 to the 10th per cubic centimeters. This means the product N times P is equal to 1.21 times 10 to the power 20th per square cubic centimeters. Now we consider an N-doped silicon material. We incorporate a density of phosphorus atoms in the lattice, which we call Nd. We assume that all donors give a free electron to the lattice. So it means the electron density N0 is equal to Nd. Now we can calculate the hole density P0. The law of mass action tells us at a given temperature, the product of the electron density and the hole density is constant, independent of doping. So P0 is equal to the square of the intrinsic charge carrier density divided by the electron density N0. The same is valid for p-doped silicon materials. We incorporate boron atoms with a density Na in the silicon network. We assume that all acceptors take one electron and therefore create hole density P0 equal to the acceptor density Na. This means that the electron density N0 is equal to the square of the intrinsic charge carrier density divided by the hole density P0. Let's take an example. We incorporate 10 to the 16 per cubic centimeters phosphorus atoms in the lattice, or in other words, we have a donor density Nd of 10 to the 16 per cubic centimeters. As we assume that all donors give a free electron to the lattice, the electron density N0 is equal to the donor density Nd. Now we can calculate the hole density P0. So P0 is equal to the square of the intrinsic charge carrier density divided by the electron density N0. So the hole density is given by 1.21 times 10 to the 20 divided by the number 10 to the 16, and then we get the hole density of 1.12 times 10 to the 4th per cubic centimeters. Now we consider a third approach to excite charge carriers, which is by light absorption. Let's consider the electronic band diagram again, and a photon with an energy equal to the band gap, indicated by the green arrow. This photon can be absorbed in a semiconductor material and can be used to excite an electron from the valence band to the conduction band. So light can make a semiconductor material more conductive. However, if we have a photon with an energy smaller than the band gap, this photon is lacking the energy to excite an electron from the valence band to the conduction band. This photon cannot be absorbed by the semiconductor material. Another situation is when the photon has an energy much larger than the band gap. This photon can excite an electron at an energy level deeper in the valence band into the conduction band, or an electron to a higher energy level into the conduction band. In these situations, the hot electrons or holes very fast relax back to the lower energy positions. For the electron, this is the bottom of the conduction band, and for the hole, this would mean the top of the valence band. This extra energy is released as heat, and will heat up the semiconductor material. So the rest energy, which is the photon energy minus the bandgap energy, ends up as heat. Finally, in this block, I would like to discuss how light absorption affects the charge carrier density in doped materials. Let's consider again the situation with a density of majority charge carriers of 10 to the 16 per cubic centimeters, and density of minority charge carriers of 10 to the 4th per cubic centimeters. Now let's assume we generate electron-hole pairs by light absorption. We generate 10 to the 11th electron-hole pairs per cubic centimeters. What will happen to the density of the majority and minority charge carriers? So we will simply add up the numbers. What you can see is that the majority charge carrier density is not affected by the light absorption. 10 to the 11th is much smaller than 10 to the 16th. On the other hand, the density of minority charge carriers is drastically affected. 10 to the 11th is much larger than 10 to the 4th. Its density is increased with 7 orders of magnitude. This is an important conclusion which we'll need later to understand the working principle of solar cells. In doped semiconductor materials, light absorption has only effect on the density of the minority charge carriers. Summarized, in this block we have discussed how to excite charge carriers in a semiconductor material by temperature, doping and light absorption. The next question is, how do those charge carriers move around and what makes them move around in a semiconductor material? I will talk about that in the next block, where we are going to discuss transport of charge carriers. What are the charge carrier transport principles? In this block, the two transport mechanisms will be discussed: diffusion and drift. We will discuss that for net movement of charge carriers, either a concentration gradient is required or an electric field is required. Let's consider a free gas of particles at a temperature larger than the absolute zero. In case of a free electron gas, these particles are electrons. The particles have kinetic energy and can move around freely. All particles move around in a so-called random walk. They move in random directions until they collide with another particle. After the collision, both particles will move in a different direction and the velocity of the particles is changed. In a free electron gas, the interaction of the particles is ruled by Coulomb-Coulomb interactions. The particles not really collide into each other, but they bend each other trajectories. Let's consider the situation that the density of the particles is uniformly distributed. No density gradient exists. On average, the particles with a random walk will have no net movement. Just as many particles will move to the right will be moving to the left. Just as many particles will be moving up as will be moving down. Now we consider a non-uniform particle distribution. At the right you see that the particle density is higher than at the left. In other words, a density gradient is present going from right to left. If these particles all move randomly around, the flux of particles to the volume with lower density on the left will be higher. The flux of particles to the volume with higher density on the right will be smaller. There will be a net movement of particles until the density is uniformly distributed. In the current situation, the density is uniform. No gradient exists, so there's no net movement of particles due to diffusion. The net movement of particles induced by density gradients is called diffusion. It can be described by Fick's law of diffusion. Je in this case is the electron current density expressed in current per area. Q is the elementary charge. D is the diffusion coefficient of the electrons, and dN dx represents the density gradient in direction x. The fusion of electrons results in a net movement of electrons to the location with lower electron densities. The fusion will be present as long as there is a density gradient. The same equation is valid for holes. The fusion of holes results in a net movement of holes to the location with lower hole densities. Now we move to the second transport mechanism, which is called drift. Charged particles like electrons and holes can also be moved under influence of an electric field. Let's consider an electric field which points to the left. If a positively charged hole is positioned in this electric field, it will experience an electric force in the direction of the electric field, so in this case to the left. Consequently, it will start moving in that direction. A negatively charged electron will experience a force in the opposite direction of the electric field. The electron will start moving to the right. The current density induced by an electric field is given by the product of the density of electrons N, the electron charge Q, the mobility constant mu, and the electric field E. Similar, the whole current density induced by an electric field is given by the product of the density of holes P, the electron charge Q, the mobility constant mu, and the electric field E. The presence of an electric field can also be represented in an electronic band diagram. Let's consider again an electric field pointing to the left. In the figure, you can see a conduction and valence band. The electric field induces a slope over the valence band and conduction band. The slope of the electronic band is positive in the direction of the electric field. It is important to remember that the excited electrons in the conduction band will on average always move down the slope of the conduction band when a slope is present. The holes will on average always move up the slope of the valence band. These are the two mechanisms which are responsible for charge transport in solar cells. Holes and electrons have net movements due to either a density gradient, which we call diffusion, or an electric field. In the previous block, we discussed that we can excite electrons and holes by absorption of light. However, holes and electrons also suffer from loss mechanism. If an excited electron and hole meet each other, they are able to recombine. They join each other and lose their mobile states, or in other words, the electron is glued again to the background in a molecular orbital. We can distinguish three types of recombination mechanisms. The first one is radiative recombination. An electron and hole recombine together. The energy released is sent out in the form of a photon. As it costs at least the energy of a band gap to excite an electron and hole pair, radiative recombination sends out a photon with at least the energy of the band gap as well. The second recombination mechanism is Auger recombination. The energy released by the recombination of an electron-hole pair is transferred to a neighboring free electron in the conduction band. This electron is excited to a higher energy level in the conduction band. This hot electron will lose its energy again as heat to the lattice of the semiconductor. The third recombination mechanism is Shockley-Reed-Hall recombination. Semiconductor materials can have various types of defects in the lattice. These defects can have energy states in the forbidden band gap, like we have seen for donor and acceptor states in the case of doping. An electron can be trapped in such defect state. If then freely moving around holes can find these trapped electrons, they can recombine as well. The loss mechanism, like recombination, determines the lifetime of the charge carriers. If the recombination rate is high, the lifetime of charge carriers is low. The diffusion length, L, is the average distance the excited charge carriers can move around and is determined by the lifetime of the charge carriers. If the recombination rate is high, the diffusion length will be shorter. When the recombination rate is low, the diffusion length will be longer. The diffusion length and the lifetime are related with a relatively simple equation. L is the square root of the product of d and tau, where d is the diffusion coefficient and tau is the lifetime. Now let's consider a p-doped semiconductor material. The holes, the blue dots, are the majority charge carriers and the electrons, the red dots, are the minority charge carriers. The holes have a small probability that they will meet an electron, and therefore the recombination rate for holes is small. On the other hand, the electrons have a high probability to meet one of the holes, as the hole density is many orders of magnitude higher. This means that the recombination rate for the electrons is high, or in other words, the diffusion length of the electrons, Le, is shorter than that of the holes, Lh. Let's consider now n-doped semiconductor materials. The electrons, the red dots, are the majority charge carriers, and the holes, blue dots, are the minority charge carriers. The electrons have a small probability that they will meet a hole, and therefore the recombination rate is small. On the other hand, the holes have a high probability to meet one of the electrons, as the electron density is many orders of magnitude higher. This means that the recombination rate for the holes is high, or in other words, the diffusion length of the holes, LH, is shorter than that of the electrons, LA. Important to remember is that in a doped material, the minority charge carriers have a short diffusion length in reference to the majority charge carriers. So, now we know how to excite charge carriers. We know how to manipulate the semiconductor material to create majority and minority charge carriers. And we understand the transport mechanism of charge carriers. It is time to build a solar cell using these tools. We will do that in the next block.
Finally, we are going to build a solar cell. Most solar cells are based on a p-n junction. The question is, what is a p-n junction? Again, we take as an example the case for silicon. We have introduced the fact that semiconductors can be doped, n-type and p-type. In the n-type material, the majority charge carriers are electrons, and the doping atoms that donated an electron are fixed positively charged in the network. In a p-type material, the majority charge carriers are holes, and the doping atoms that accepted an electron are fixed negative charges in the network. On the left, we see a p-type semiconductor material. The electronic band diagram of the p layer is illustrated on the left as well. I would like to address again that for the p-type silicon, the Fermi level, indicated by the dashed black line, is closer to the valence band than to the conduction band. On the right, we see the n-type semiconductor material. Its corresponding electronic band diagram is illustrated on the right. The Fermi level is closer to the conduction band for the n-type material. Now we glue the n-type and p-type semiconductor materials together. And this is what we call a p-n junction. In reality, we take one piece of silicon material in which we intentionally dope one part p-type and the other part n-type. Now we first consider the situation that this p-n junctions is in the dark and is in thermal equilibrium. What will happen? How will the charge carrier be distributed over the p region and the n region? On the left, we have a majority of holes. On the right, we have a majority of electrons. As we obviously can see, the p-n junction has an enormous density gradient close to the interface between the p and n region. The hole density is much lower in the n region than in the p region, whereas the electron density is much lower in the p region than the n region. As we discussed earlier this week, diffusion is driven by density gradients. So let's assume that the charge carriers diffuses until the point that the electron and hole densities are equally distributed over the p region and the n region. The question to you is, will this really happen in nature? Let's take a moment to think about it. Will this happen? The answer is no. But why not? Because we have not considered the second transport mechanism, which is based on the electric field, drift. Let's consider the homogeneously distributed charge carriers as shown here. Are the p region and the n region neutrally charged? The answer is no. The p region is negatively charged. Although there are just as many holes as electrons, there are still many fixed negatively charged acceptor atoms in the background. The other way around, the n region is heavily positively charged. Although there are just as many holes as electrons, there are still many fixed positively charged donor atoms in the background. So this charge will create a strong electric field from the n region to the p region. This internal field over the depletion zone pushes holes back to the p region and the electrons back to the n region. So, what happens in reality? At the interface region, some holes will diffuse to the n region and some electrons will diffuse to the p region. As the diffusion length of holes in n-type is short, they will soon recombine with one of the majority electrons. The same is valid for the electrons. As the diffusion length of electrons in p-type is short as well, they will soon recombine with one of the majority electrons. As a result, there is a small region around the p-n interface in which all charge carriers are wiped out. In this region, the only charges present are the charges related to the background, donor and acceptor atoms. This region is called the space charge region. We also use for this region the term depletion zone. The space charge region is depleted from mobile charge carriers. In this example, the left side of the space charge region, facing the p-type side, is negatively charged, whereas the right side of the space charge region, facing the n-type side, is positively charged. This results in an electric field across the space charge region, which is directed from the n-type region to the p-type region. This will induce an opposite movement of charge carriers in reference to the diffusion. The electric field at the space charge region will force the minority charge carriers in the p region, the electrons, to move to the n region, whereas the electric field will force the minority charge carriers in the n region, the holes, to move to the p region. So we are considering at the moment a p-n junction that is in the dark and is in thermal equilibrium. The two transport mechanisms over the space charge region are in balance. We have introduced two simple equations for the drift and the diffusion earlier this week. The diffusion current density for electrons is ruled by the density gradient, which is the electron density at the n region minus the electron density in the p region. The electrons are the minority charge carriers in the p region, which means that the density gradient is fully determined by the majority electron density in the n region. The same is true for the holes. The diffusion current density for holes is ruled by the density gradient, which is the hole density at the p region minus the hole density in the n region. The holes are the minority charge carriers in the n region, which means that the density gradient is fully determined by the electron density in the n region. With other words, the diffusion is controlled by the majority charge carriers in the p and n region. It's important to realize that you can vary diffusion current density in two different ways. As the diffusion scales with the gradient dP dx or dN dx, you have either to increase the density of the majority charge carriers, in this case dP, or you have to change the width of the depletion zone, dx. In the following final block of this week, I will show that you can manipulate the width by putting a voltage bias over the solar cell. Diffusion is controlled by the density of the majority charge carriers. To the contrary, the drift works on the minority charge carriers. The electric field will force the electrons in the p region, where the electrons are the minority charge carriers, to move back to the n region. Similar, the electric field will force the holes in the n region, where the holes are the minority charge carriers, to move back to the p region. So the drift is controlled by the minority charge carrier density. Increasing the drift current density can be accomplished by either increasing the density of the minority charge carriers, in this case P, or by increasing the electric field E over the depletion zone. In this example, the p-n junction is in thermal equilibrium. The current density at the depletion zone are in equilibrium. If you would connect the left side of the p region and the right side of the n region with an electrical circuit, we would have no current flowing through the circuit. The electrical field will create a built-in voltage over the space charge region. The origin of the built-in voltage can be demonstrated by looking at the electronic band diagram of a p-n junction. In a p-n junction, in thermal equilibrium, the Fermi level is constant across the entire junction. I will try to visualize this using a simple explanation. You can compare the Fermi level in a junction under thermal equilibrium with that of water level in a water tank consisting of two reservoirs. The two water reservoirs are separated with a barrier. The left one has a lower water level and the right reservoir has a higher water level. Let's say the left side is the p region with a Fermi level close to the valence band, and the right side is an n region with a Fermi level further away from the valence band. If we remove the barrier between the both reservoirs, the water levels will equalize over the two reservoirs. The same is applicable for the Fermi level. Important to know is that the relative position of the electronic bands like the conduction and valence band to the Fermi level remain the same. This means that the mechanism of equalizing the Fermi level will move and bend the conduction and valence band. This is demonstrated in this animation. If we equalize the Fermi levels, the conduction and valence band are bended in the depletion zone. We see that in thermal equilibrium, the valence and conduction band have a steep slope across the depletion zone. As discussed earlier, a slope in an electronic band diagram represents an electric field. The electric field across the depletion zone is equal to Q times VBI. Q is the charge of the hole or electron. VBI is the built-in voltage over the depletion zone. This slope will make the minority electrons move from the p region to the n region, whereas the minority holes in the n region will go up to the slope of the valence band to the p region. Now we have discussed a p-n junction in thermal equilibrium in the dark, in which diffusion and drift are in balance. However, we can manipulate this equilibrium by first applying a bias voltage over the p-n junction. Secondly, we can manipulate this equilibrium by illuminating the p-n junction to increase the minority charge carrier density. In that case, we have created a solar cell. The working principle of the solar cell will be revealed in detail in the next final block of this week. We have discussed a p-n junction in the dark in thermal equilibrium. In this situation, the diffusion and drift over the depletion zone are in balance. Now we are going to disturb the equilibrium by applying a bias voltage or shining light on the p-n junction. We will see that an illuminated p-n junction acts like a solar cell. First, we consider a p-n junction in the dark and we apply a forward bias on the device. This means we have a more positive voltage at the p region side than at the n region side. The depletion zone is the area where the built-in electric field is present. It is also the zone with the highest resistivity, and the applied external bias will create an additional electric field at the depletion zone, indicated by the green arrow. This additional field, indicated by the green arrow, is opposite to the built-in electric field indicated by the black arrow. The effective electric field across the depletion zone is the sum of the built-in field and the applied electric field, and becomes smaller as a result of the forward bias. As a consequence, the width of the depletion zone is affected. The width becomes much narrower. This means that the diffusion becomes more dominant than drift. You can easily see this if you look in more detail to the equations for the current densities related to diffusion and drift. First, since the width of the depletion zone is smaller, or in other words, dx is getting smaller, the density gradients dn dx and dp dx become much larger. As a consequence, the current density related to diffusion becomes significantly larger, indicated by the larger arrows. On the other hand, the electric field E is reduced, which means that the current density related to drift is getting slightly smaller. Note that the effect of the increased flux due to diffusion is much larger than the small change in drift. This means that we generate a net current over the depletion zone. More electrons are diffusing from the n region to the p region than are drifting from the p region to the n region. More holes are diffusing from the p region to the n region than are drifting from the n region to the p region. This means, by applying a forward bias over a p-n junction in the dark, we produce a net current through the electrical circuit. The contact and wires of an electrical circuit consist of highly conductive metals. In metals, the charge carriers are free mobile electrons. This means that the electrons move through the electrical circuit from the p side to the n side. At the n side, electrons are injected in the n region again. Applying a forward bias on the p-n junction can be illustrated using the electronic band diagram of a p-n junction. The forward bias reduces the electric field over the depletion zone. This results in a reduction of the slopes across the depletion zone in the conduction and valence band. The p-n junction is not in equilibrium anymore, and the Fermi level. This results in a splitting of the Fermi level in the depletion zone, which are called quasi-Fermi levels. The upper level represents the population of electrons, and the lower level represents the population of holes. In equilibrium, these distributions are mirrored and related by the Fermi-Dirac function as discussed in block 2.4. However, by applying a forward bias over the p-n junction, the system is not in equilibrium anymore and the population of holes and electrons become more complex. The energy gap between both quasi-Fermi levels is Q times V, in which Q is the charge of electrons and holes again, and V represents the forward bias applied on the junction. Due to the reduced field, or in other words, the reduced slope, the drift of electrons and holes is reduced. In addition, the reduced width of the depletion zone enhances the diffusion. We can do the opposite of forward biasing as well. We can apply a reverse bias over the p-n junction, which is still in the dark. The voltage at the contact of the p-doped side is negative and the voltage at the contact of the n-doped side is positive. The built-in electric field, indicated by the black arrow, and the applied electric field across the depletion zone, indicated by the green arrow, are now pointing in the same direction. The total electric field of the depletion zone is increased. As a result, the width of the depletion zone is getting much wider, or in other words, the X is getting larger. This has the opposite effect on the balance between diffusion and drift. The density gradient is becoming smaller, so both density gradients dN dx and dP dx are getting smaller because the X is getting larger. The current density related to diffusion of both electron and holes is reduced. The drift is enhanced. Since the electric field E is larger, the drift of electrons and holes is slightly enhanced. In this case, the drift current density is dominating the diffusion current density. Since the drift current density is ruled by the density of the minority charge carriers in the P and N region, the total net current is extremely small. In the reverse bias condition, an extreme small current will move from the contact at the P region to the N region. This means that on average, electrons are walking from the contact of the N region to the P region. Summarized, in the dark on the forward bias, the diffusion of charge carriers of the depletion zone is dominant, whereas on the reverse bias, the drift of charge carriers of the depletion zone is dominant. On the forward bias, in the dark, the PN junction can produce relatively large currents, whereas in the reverse bias, it generates very small currents. Such a device is called a diode. It has a high conductance in forward bias, but has a low conductance in reverse bias. Now we are going to shine light on the device. This means that we are looking at a solar cell. Light is incident from the left on the P region. For the moment, we assume the light is being absorbed in the P region and the N region. The absorption of the photons will generate electron and hole pairs. Important to realize, and as discussed earlier, light absorption only affects the density of the minority charge carriers in doped semiconductor materials. This means that the light-excited charge carriers significantly increase the density of the electrons in the P region and the density of the holes in the N region. Subsequently, we increased the drift. This can be easily recognized by looking at the equation for the current densities, as we see that we are significantly increasing the drift over the depletion zone, which is indicated by the larger arrows. Many electrons drift from the P region to the N region, and many holes drift from the N region to the P region. The current density related to the drift can be easily increased by many orders of magnitude under illumination in reference to the PN junction in the dark. By illuminating a PN junction, we can generate a current. Finally, we're looking at the working principle of a solar cell. Using an electrical circuit, we connect the contact at the p-doped silicon with that of the n-doped silicon. Or in other words, we short-circuit the PN junction. In this condition, the illuminated PN junction will produce only an electrical current. We call this current the short-circuit current of a solar cell. We can make a very simplified animation of the journey of the generated charge carriers. On average, a minority electron will drift to the N-type material and diffuse to the metal contact at which the electron is injected. The electron moves to the contact at the P site and is injected into the P-type silicon. Here it quickly recombines with a hole. The minority holes in the P-type drift across the depletion zone and diffuse to the back contact to recombine with the electron. However, no current is created when we open the electrical circuit. In that case, the dominant drift current of light-excited charge carriers will positively charge the P region with holes and negatively charge the N region with electrons. This charging creates an electric field opposite to the built-in electric field and reduces the net drift current again. This charging of free holes in the P region and free electrons in the N region will build up until both the drift currents are in equilibrium. This means that the device does not generate a current, but builds up an electric field, or voltage. The voltage created by an illuminated solar cell under open circuit conditions is called the open circuit voltage. Summarized, by illuminating a PN junction, we can generate under closed circuit conditions a current and under open circuit conditions a voltage. So the PN junction is a device which facilitates the photovoltaic effect. As discussed in the first week, the photovoltaic effect has three essential steps: generation of electron-hole pairs due to light absorption, separation of electrons and holes, collection of electrons and holes at the contacts. Step 1 takes place in the semiconductor material, step 2 occurs at the space charge region, and step 3 takes place at the terminals. We now are familiar with the working principle of a solar cell. Under week 2, you will find a collection of exercises which helps you further in the understanding of semiconductor materials, charge carrier transport, and PN junction. Next week, we will look how we can determine the performance of solar cells using external parameters like the short circuit density and the open circuit voltage. And we will discuss some design rules how to optimize the performance of solar cells. So see you next week.
Okay.